Clocks in the machine, RoPE and ALiBi. Inside every large language model, a system of clocks is ticking. The fast ones measure grammar. The slow ones, the meaning of an entire document. Today I'll show you how these clocks work and why they came to dominate the entire AI industry. This episode covers two methods of encoding token positions in a sequence. The first is RoPE, Rotary Positional Embeddings, a system of rotating clocks. The second is ALiBi, attention with linear biases, a simple ruler that penalizes distance. Both methods solve the same problem. The transformer processes tokens in parallel. Without an additional signal, it has no idea which token is first and which is the 100th. The previous episode in this series covered Vaswani's sinusoids and learned positional embeddings. Both of those approaches are absolute. They assign each position a fixed vector. Today, we go into modern solutions. Here's what you'll see in this episode. First, why adding position destroys semantics. Second, how the mathematics of complex numbers solves that problem. Third, a system of clocks running at different speeds. Fourth, ALiBi as a simpler alternative. And finally, why the clocks beat the ruler. The problem. Addition corrupts semantics. Traditional positional encoding works through addition. You take the token vector, you take the position vector, you add them together, the result goes into the attention mechanism. The problem is that this operation changes the length of the vector. The length of a vector encodes semantic information. It captures what the token means. Describe this precisely. By adding positional information directly to the token embedding, you contaminate semantic information with location information. The model has to spend capacity untangling meaning from position. That's a waste of resources. In natural language, what matters is relative distance, not absolute position. The relationship subject is 3 tokens before the predicate carries identical meaning at position 5 and at position 5000. That's the key observation. Let's formulate the mathematical requirement. We're looking for a positional encoding where the dot product of query and key vectors depends only on the content of the tokens and the distance between them, never on absolute positions. That's a strict equation, and it turns out there is exactly one solution. Before we understand the clocks, we need to understand that solution. RoPE, rotation instead of addition. The solution comes from the mathematics of complex numbers. RoPE is not a heuristic or an approximation. It's the unique solution to a strictly defined mathematical problem. I'll walk you through the derivation in 5 steps. Step 1. We treat pairs of vector dimensions as complex numbers in polar form. Every complex number has 2 properties: magnitude, meaning length, and phase, meaning angle. Step 2. The relative position requirement implies that magnitude and phase satisfy separate conditions. The magnitude is the product of the query and key magnitudes. The phase is the difference of their phases. Step 3. And this is the key insight. Substituting the boundary conditions, we prove that magnitude is independent of position. That means exactly one thing. Rotation preserves the norm of the vector. The semantic information, what the token means, remains intact. Step 4. The phase increment between consecutive positions must be constant. The phase at position m equals m times theta, not an arbitrary choice. It's the only solution to the equation. Step 5. The final result. We encode position by multiplying the vector by e to the power I times m times theta. Multiplying by this quantity is a rotation of a two-dimensional vector by angle m theta. Position encoded as a rotation angle. The vector's length doesn't change. Now, the moment that ties everything together. When we compute the dot product of the rotated query and key vectors, the rotation matrices subtract out. R of m transposed times R of n equals R of n minus m. The absolute position disappears. Pure distance between tokens remains. This isn't an approximation. It's a mathematical proof. The derivation shows the solution for a single pair of dimensions. Vectors in LLM models have hundreds of dimensions. The answer: a system of clocks running at different speeds. The clock system, from grammar to document meaning. RoPE divides a d-dimensional vector into d over 2 pairs. Each pair is rotated independently with its own frequency theta I. The frequencies form a geometric sequence, from theta close to 1, meaning fast rotation, to theta close to 0.0001, meaning very slow rotation. Here's what that means in practice. Imagine a system of clocks. Fast clocks, low dimensions, encode grammar and syntax. They distinguish adjacent tokens. Their cycle closes over roughly 6 tokens. Medium clocks encode paragraph structure, references within a few hundred tokens. Slow clocks, high dimensions, track the meaning of the entire document over tens of thousands of tokens. Every token gets a unique timestamp, a combination of positions across all clock hands. The attention mechanism looks only at the difference between clocks, relative position, not the time itself, not the absolute position. The Llama model, with its 4096 dimensions, has 2048 independent clocks, each ticking at a different speed, from second hands measuring grammar to hour hands tracking the narrative of an entire book. One important technical detail. RoPE is applied in every attention layer, to the query and key vectors, never to value. The average dot product value naturally decreases as the distance between tokens grows. This gives the model a natural inductive bias. Closer tokens have more influence, consistent with how language works. Someone, however, proposed something radically simpler: a ruler instead of clocks. ALiBi, a ruler instead of clocks. ALiBi represents a completely different philosophy. Zero positional embeddings, zero modifications to query or key vectors, zero learned parameters. The only modification is a bias added to attention scores after computing the dot product, a simple penalty proportional to distance. The farther the token, the larger the penalty. After softmax, this translates to exponential dampening of attention. Each attention head has a different penalty coefficient, a slope. The slopes form a geometric sequence. For 8 heads, the values are 1/2, 1/4, 1/8, down to 1/256. This distribution forces specialization. Heads with a large slope are syntactic microscopes. Strong distance penalty, focus on neighboring tokens. Heads with a small slope are semantic telescopes. Mild penalty, global context visibility. Together, they form a multi-scale ensemble. Radical simplicity. Research on the Bloom model revealed a systematic pathology. ALiBi causes collapse in 31 to 44% of attention heads. These heads direct nearly all their attention toward the sequence's start token. Reinitializing those heads temporarily improves performance, suggesting that aggressive distance penalties have unintended consequences in deep networks. Adoption of ALiBi was limited to the Bloom, MPT, Bloomberg GPT, and Falcon 7 billion and 40 billion models. Since 2024, no new significant model has chosen ALiBi. Falcon's second generation switched from ALiBi to RoPE, which closed that chapter. ALiBi had one key advantage: native context extrapolation. RoPE does not natively extrapolate. That weakness could have decided the fate of the entire technology. The context race, from 4,000 to 2 million. RoPE doesn't natively extrapolate. Rotation angles outside the training range generate unpredictable signals. Researchers showed that attention scores explode above 8,000 tokens beyond the training range. The industry responded with a cascade of scaling methods. The first method, position interpolation, abbreviated PI, instead of extrapolating, it compresses positions into the original range. Position 8192 maps to 2048 at a 4 times extension. Simple, but it destroys local grammatical patterns. Compressing all frequencies uniformly is too blunt. Enter the development that changed the industry. An anonymous Reddit user with the handle block97 posted 3 lines of code. Instead of scaling positions, they changed the frequency base theta. High frequencies, local grammar, preserved. Low frequencies, global context, interpolated more aggressively. The method was named NTK-aware scaling. It works without fine-tuning. 3 lines of code. The next step, yarn, an extension of NTK. Dimensions are categorized into 3 groups. High frequencies left untouched. Low frequencies interpolated. Between them, a smooth ramp. Plus temperature scaling, so attention doesn't spread thinly across too many tokens. Yarn requires 10 times fewer tokens than PI. Extension to 128,000 tokens. And finally, LongRoPE, the first extension to 2 million tokens. Evolutionary search for optimal scaling coefficients for each dimension separately. Integrated into Microsoft's Phi-3 model. Llama version 3.1 raised the theta base 50-fold, from 10,000 to 500,000. The reason? At the original base and 128,000 tokens, the slow clocks would complete a full rotation. A token at position 128,000 would have an identical timestamp to the token at position 0. That's aliasing. The increased base eliminates it by slowing the rotation. There's one finding that applies to all methods. Low perplexity doesn't guarantee effective retrieval. Researchers revealed a U-shaped curve. Models handle information at the beginning and end of context well. They lose a significant portion of their effectiveness in the middle. The lost in the middle effect applies to all models regardless of positional encoding method. Scaling methods gave RoPE something ALiBi never needed. They also eliminated the only advantage ALiBi had. One question remains. Why did the simpler method lose? Why the simpler method lost ALiBi didn't lose? Because it's technically inferior. Its native extrapolation is better. It lost because Meta chose RoPE for the Llama model. And Llama triggered the snowball effect. Mistral, RoPE. Gemma, RoPE. Qwen, RoPE. DeepSeek, RoPE. Falcon second generation switched from ALiBi to RoPE. Yi, Phi, RoPE. The tooling followed adoption. Flash attention, VLLM, Hugging Face with the RoPE scaling parameter. The entire ecosystem optimized for RoPE. The scale of dominance is enormous. Dozens to over 20 model families with RoPE against only a handful with ALiBi. Ecosystem beat elegance. This isn't the first time in the history of technology. The technically superior method loses when its rival builds infrastructure, tooling, and a community around itself. ALiBi had simplicity. RoPE had Llama. The trend in 2025 points toward hybrid architectures. Command R7 billion combines RoPE layers with sliding window attention alongside layers without positional encoding, so-called NoPE, with global attention. Gemma, third generation, uses a different strategy, alternating local and global attention, both with RoPE but with different databases, 10,000 for local attention and 1 million for global. These two approaches represent different philosophies of hybridization. The common denominator, abandoning the assumption that a single positional encoding method must dominate all layers of the model. The clocks in the machine beat the ruler, not because they're more elegant, because the industry built an entire ecosystem around them. Key takeaways. 3 things to take away from this episode. First, rotation preserves semantics. It's the only correct solution to the problem where the dot product depends exclusively on relative position. Additive encoding contaminates semantics with position. Rotation doesn't. Second, a system of clocks running at different speeds encodes position at every scale, from grammar to the meaning of an entire document. Every token gets a unique timestamp, and attention looks only at the difference between clocks. Third, ecosystem beat elegance. RoPE won not through mathematical superiority, but through the llama snowball effect and mature tooling. If this episode helped you understand how models encode position, leave a like and subscribe to the channel. In the next episode, we go deeper into the architecture, encoder, decoder, and why the difference between them determines what a model is capable of. Thank you for watching. See you in the next episode.